So where we last left off, we were discussing drawing constitutional isomers. We gave an example for ethylamine, which is the structure shown here, and we drew a set of constitutional isomers for our formula. Now, what we're now going to do is we're going to talk about how to represent structures in a bond line format. This is the common way structures are drawn in organic chemistry. It saves time, saves energy, and it efficiently conveys structural information. So in bond line structures, bonds are drawn in a zigzag format with each line representing one bond. So the start and end of a line represents a carbon atom. So for example, this carbon-carbon bond would just be represented as a line, where the start and end of our line represents a carbon atom. Now, importantly, all atoms have hydrogen atoms needed to have the correct formal charge and a complete octet. And carbon typically has 4 bonds. So for example, if we're looking at this carbon-carbon bond here, how many hydrogens would this carbon need? So currently we have 2 carbons bonded together. So how many hydrogens would we need to add? 3. Yep.
Oh.
Perfect, perfect. Now, in bond line structures, lone pairs are also typically shown. So to give you an example where we talk about formal charges, and to give you an example where formal charges begin to have an influence in how we draw these bond line structures, how would we draw hydrogens on the following arrangement? So let's suppose we have a positive charge here. Let's suppose we have a positive charge here, and I'll just simplify it further. Now that we have a positive charge, how many hydrogens do I need to add to my positively charged carbon with 1 carbon-carbon bond? So if it's positively charged, is this carbon going to have more bonds or less bonds than usual?
Less bonds.
Yep, so it'll only have 2 hydrogens. Does that make sense? So just to refresh everyone's knowledge on bonding arrangements, so depending on whether you have a radical, cation, or anion, we'll have a different number of bonds and lone pair electrons for each of our formal charges. So this bonding preferences table, again, is very useful in figuring out the number of implied hydrogens. Okay, so bonds are drawn to reflect the geometry of a molecule. So single bonds are drawn in a zigzag format. The reason for that is that carbon is tetrahedral, and this zigzag format tries the best that it can to represent our 109.5 degree angles. So that's why we draw our bonds in a zigzag arrangement. Double bonds are drawn with 2 lines, and because a double bond has a different bond angle, remember how we discussed Vesper theory and double bonds have 120 degree angles, we want to make sure that our line structures represent that. So we draw our double bond with 2 lines. So this is our double bond, otherwise known as an alkene. And as we notice, when we draw a double bond, the geometry of our double bond is represented in our line structure. Does that make sense to everyone? And this will serve you well in helping you understand the shape of these organic molecules. And shape is really important when it comes to reactivity and accessibility. So triple bonds are drawn with 3 lines and are linear. They have 180-degree angles. So for example, if we have the following structure that contains a triple bond, so if we have the following structure that contains a triple bond, as we notice, the triple bond has a bond angle of 180 degrees. So in our line structure, we respect the fact that we have 180-degree bond angles by drawing out our triple bond with 3 lines and then making sure that our triple bond is linear, where we have 180-degree bond angles. Does that part make sense to everyone? Does that make sense to everyone so far?
Yeah.
Perfect, perfect. So let's continue on and let's talk about some common mistakes. Whoops, let me just resize it. Let's talk about some common mistakes in drawing bond line structures. So first and foremost, one of the major mistakes is that if a carbon has a formal charge, make sure to indicate the formal charge and add the appropriate number of lone pairs. So for example, if we have the following structure, we would write, so this is represented in our bond line structure as so, where you draw your lone pair and your anion. Notice how this carbon, if it's an anionic carbon, how many hydrogens do I need to draw to that carbon? How many hydrogens do I need to draw? How many hydrogens do I need to draw?
Before.
So considering it has a lone pair and a bond already, how many hydrogens do I need to draw?
2.
2, exactly right. Because as we see, that gives us a formal charge of 4 minus 3 minus 2 of -1. Does that make sense? So if your carbon has a formal charge, make sure you label the formal charge and you explicitly draw the lone pairs, and you add the appropriate number of hydrogens to match the target formal charge. The second case that you need to be aware of, when drawing double bonds, make sure to draw the bonds as far apart as possible with 120-degree angles. So for example, in this case, as we can see, our bond angles are trying to closely represent the 120-degree bond angles observed for sp2 or trigonal planar carbons. My question to you is, for this carbon right here, how many hydrogens do I need to add? How many hydrogens do I need to explicitly draw?
E2, because it already has a double bond.
It has a double bond and a single bond.
So
So
1.
1, yep, exactly right. While these carbons at the end would need 3. The same idea in terms of geometry also applies when we are dealing with cations. So for example, the following cationic species, we try to draw the bond angle to as closely represent a 120-degree bond angle. So for this cation here, how many hydrogens do I need to add? How many hydrogens do I need to add? How many hydrogens would I need to add to this carbon right here? What was that?
Is it 1?
Yep, exactly right. And as we notice, I drew this hydrogen in a very specific way to represent the fact that we have a pretty wide bond angle of about 120 degrees. So the way that you draw your hydrogens in your structure and the way that you draw your bonds and bond angles conveys information about the bond angles found in your structure. So I really want to encourage these good habits. And just to showcase a comparison, we draw our hydrogens on our other carbon atoms like so. Does everyone notice how the bond angles are different? Does everyone notice how the way the hydrogens are drawn is different for an sp2 versus an sp3?
Yeah.
And I know this seems a little nitpicky, but it will save you a lot of grief later on if you can more appropriately start drawing the geometries earlier on in the class.
Will we start to have to be add the like the solid line and the dashes to show?
Yes, that is referring to stereochemistry, and that sort of builds on this a little bit further, where we're now just not noting bond angles, but also the relative position of the bonds in 3D space. And we'll talk about that more in chapter 5. So the next major mistake or thing to pay attention to is that all heteroatoms must be drawn with the appropriate amount of lone pairs, and all hydrogen atoms attached to the heteroatoms must be drawn. So for example, if we have this cyclic structure like so, now in some condensed structures, they remove and in some bond line structures, they don't show the lone pairs, but for this class, and in your textbook, it is common convention to write out the lone pairs for each heteroatom. Now, if your heteroatom has lone pairs attached to it, and if your heteroatom has hydrogens attached to it, then those hydrogen atoms must be explicitly noted. So in your condensed structure, you would note the attached hydrogen atom by either putting the hydrogen below the heteroatom or adjacent to the heteroatom. Other examples where this can come up would be like so. So in both cases, we've drawn out our heteroatom, we've indicated the lone pairs, and we've explicitly noted any hydrogens on the heteroatom. Does that make sense? And that's because bond line structures try to convey the most structurally relevant information in the least amount of explicitly drawn atoms as possible.
For the
So
OH structure,
yes.
Is there still a carbon on both ends of that line, or is the oxygen the end of that line?
The oxygen's the end of the line. Exactly right. So a carbon is only represented at the end of a line if there's no atom at the end of the line.
Okay.
Yeah. So in this case,
So if they're with nitrogen, it's just the carbon connecting to the nitrogen.
Exactly
and another
right.
carbon.
Exactly right.
Okay.
And to show that out explicitly, I'm going to write out the full formula for this structure. So we have CH3, CO, and then to finish off this structure, we have NH, CH3. So as we notice, the end of a line is only represented by a carbon if there's no other atom at the end of that line. Does that make sense? Did that address that question?
Yep.
Perfect. So the next major idea, if an atom is sp hybridized, make sure the bond angles are 180. In some cases, an ambiguous carbon is represented by a dot. So for example, if you have the following structure, notice how I'm drawing out my bond angles so that my bond angles are 180 degrees. In some ambiguous cases, so for example, the following structure, it's unclear whether or not we have a carbon at the center of this double bond, set of double bonds, so we note that with a dot. This this bond line structure is representing the following Lewis structure. So if a carbon's ever ambiguous, you can put a dot to explicitly note that a carbon is present. Does that make sense to everyone? Perfect, perfect. So let's try to draw a bond line structure for each of the following compounds. So I'll start us off, and you generally just process your structures from left to right. So I draw my OH. We draw each of our carbon atoms as a zigzag pattern. For our triple bonds, however, we draw our triple bond and we make sure our bond angles are 180 degrees. For double bonds, we draw our double bonds and we make sure that our double bond angle is around 120. And then we draw both of our methyl groups. So this would be a bond line structure for the above structure. So essentially all you're doing is you're replacing your carbons and you're getting rid of your hydrogens and you're replacing your carbons with just a line. Does that make sense? Does this representative example make sense to everyone? So let's have you try with the annotate feature. So again, just as a reminder, in Zoom, there's a black button at the top of your view called Meeting Options, and you can go and find the annotate feature under Meeting or View Options. So I'd like everyone to work on this second example to try writing out a condensed line structure for the following Lewis structure. And remember, for heteroatoms, you need to write the lone pairs and explicitly note the hydrogens. So don't be shy to share your responses using the annotate feature, and we'll discuss this example in about 2 to 3 minutes. And it looks good so far. Just remember to include the lone pairs on all of the heteroatoms. So the response was great so far. So allow me to just clear the annotations, and then I'll rewrite your solution in the instructor's format, just so that way it's visible when I export this document to Canvas. So as everyone correctly pointed out, and as the contributing student correctly pointed out, and the students in the chat have noted, so we replace all of our carbons with our lines. Each carbon represents a point on the line. We draw out all of our heteroatoms, and we explicitly note the number of hydrogens and the lone pairs. From that, we end up with the following complete bond line structure. One thing to note, one thing to pay attention to, because we have double bonds, our bond angles are adjusted to be around 120 degrees. Does this example make sense to everyone? Does this make sense so far?
Yeah, quick question. So
Yeah.
could we just write OH with the oxygen having two lone pairs drawn down?
Yes, that would be perfectly fine as well.
Okay, I just want to make sure.
Yeah, that would be perfectly fine as well. Any other questions on this example?
Just one. Does it have to be H2N with the lone pairs, or can it be NH2 with the lone pairs? Does it?
That's fine. I generally try to draw the hydrogens opposite to the side that the nitrogen is bonding, but that's just personal preference.
Oh, okay, just to show that the fact that they're okay.
Yep, just to show the fact that the hydrogens belong to the nitrogens. It doesn't matter what side the double bond is on. You can draw it on the top or on the bottom. That's just a matter of personal preference. So we can just as easily draw it. We can just easily draw it like so, and it doesn't make a difference. You do want to make sure you're respecting the relative arrangement of atoms across the double bond. So the methyl group and this amide functionality are on opposite sides of the double bond. So make sure when you draw your bond line structure, you aren't changing the geometry. Does that make sense? Perfect. So let's keep going now, and let's try to draw a bond line structure for some anionic species. So these are charged species. So I'll start us off with this first example. So in this case, I'm going to convert all of my carbons into lines. If there's an explicitly drawn lone pair, I'll draw the lone pair and note the charge. For all my heteroatoms, they're explicitly drawn with lone pairs. And then again, we want to make sure that we're respecting the bond angles found in this structure. So this gives us the following bond line structure for this molecule shown. Notice how I corrected my triple bond so that my triple bond now has an appropriate 180 degree bond angle. Does that make sense to everyone? Any questions on this example? If not, let's keep going now, and I'd like you now to work on drawing bond line structures. I'd like you to work on drawing bond line structures for the following for the following two molecules. So let's spend about 4 to 5 minutes on this example, and let's draw bond line structures for each of these examples. And don't be shy to share your responses using the annotate feature, which is found in the view options tab, which is the upper little black drop-down menu in the Zoom view. So don't be shy to share your proposed bond line structures, and I'll be happy to provide feedback. and we'll discuss in about another 3 to 4 minutes. Well, let's try to get some responses shared using the annotate feature and in the chat, just so that way we have something to build off of. And don't be shy while one of your classmates is drawing one structure to try to chime in and draw a bond line structure of your own, or draw a bond line structure for another structure on this list. And the first structure we see looks great. Looks great.
Is a normal case where carbon's going to be seen as ambiguous only when it's going to be double bonded to something on both sides? Or like, for example, in the first structure where it has this lone pair and a formal charge, could we use a dot to signify that's also a carbon, or is that just not needed?
That's not needed, because the fact you have a lone pair assigned to that position implies that you have a carbon at that position if you don't have any other atom label. Yeah, so that carbon is implied to be present, not only because it's at the intersection of lines, but because a lone pair is also present.
Gotcha. Okay.
Perfect, perfect. So the structure I see down here, it's on the right track. It's on the right track. But remember, the carbon is at the intersection of the lines, and then you put your lone pair adjacent to that carbon. So looking at the proposed structure, it's good. There just needs to be a small change in formatting. So let's address each of these examples, and I'll write my instructor key just so that way, if you're looking back on the note set in Canvas, you have the structures drawn in a compatible way so it's exported. So we replace each of our carbons with a line. We explicitly draw out each of our heteroatoms with lone pairs. We draw hydrogens attached to heteroatoms. And since our carbon has a negative formal charge, we draw out our lone pair and we indicate the formal charge. So this is the complete bond line structure for the following molecule. Let's look at this next example now. So we're asked to draw a bond line structure. So we clearly replace each of our carbons with a line. We draw out each of our heteroatoms, and we note any lone pairs attached to our heteroatoms. Additionally, for carbon, if it has a formal charge, we draw our lone pair and we explicitly note the formal charge. Make sure to draw your lone pair adjacent to your carbon, and make sure that your lines are connecting between your carbon atoms. That minor stylistic reformatting compared to the student solution would give you a perfectly correct response. I definitely understood what you were trying to convey, but just make sure you put the lone pair adjacent and that you draw your lines connected together, because the carbons are at the intersection points of the lines. Does that make sense? But that contribution was very good, and I greatly appreciate the student contributions that we're receiving so far. And again, don't be shy to break out the annotate feature for any of these problems. There's plenty of space on the whiteboard.
Do you
Any
have to include the formal charge of nitrogen?
Yes, so we note the formal charge in this case as plus. Exactly right. Any other questions on this example? Okay, let's keep moving on then. So in this case, we're asked to draw a line structure from the condensed structure. So often what I like to do is to write out a partially condensed structure and then convert it into a line structure. So in this case, I have CH3, CH2, O, CH2, and then this CO2H is a carboxylic acid. And I know a carboxylic acid looks something like this. So now that I have my partially condensed structure, now I can get to work in writing my line structure. Of course, if you're able to skip straight to the line structure, you're more than welcome to do so. But I find tackling these problems step by step can often save you a lot of trouble. So here we go, and this is our final bond line structure for the following condensed structure. Does this make sense to everyone?
Is it common to end up with a stereoisomer if you started with a down line instead of an up angle line?
So in terms of stereoisomers, so stereoisomers occur when you have a carbon with 4 different substituents. So in this case, we do not have any stereocenters. So we don't have any explicit stereocenters, but your point is well taken in that if we wanted to convey a stereocenter, we'd have to use dash wedge notation. So the bond line notation isn't conveying stereochemistry except for an alkene where you have to make sure that you're respecting the alkene geometry. Did that answer your question?
Yeah.
Perfect. So to repeat this process, I take my condensed structure and I convert it into a partially condensed structure. Once I have my partially condensed structure, I draw each of my carbons as the start and end of a line. I draw out explicitly each of my heteroatoms, and then I explicitly draw out all of my hydrogens on my heteroatoms. Did that answer the question in the chat? Did that clarify the process? Perfect. So let's apply what we've learned. And let's draw out a bond line formula for the following structure. Remember, go from your condensed structure to your partially condensed structure, and then you draw your bond line. So let's spend about 2 to 3 minutes on this example, and don't be shy to share your responses in the chat. And again, don't be shy to break out the annotate feature, and I'll be happy to provide feedback. So the structure looks pretty good. One thing to keep in mind is make sure your carbon count matches the original structure. So the structural motifs you had were perfect. You're just missing one carbon. You're on the right track there. You're on the right track there. Yep, perfect, perfect. So let's clear this and now let's provide the instructor solution. So first things first, I really like to write out my partially condensed structure. So again, my CH has one less hydrogen than usual. So these CH3 groups are bonded both to this CH functionality. So I draw my CH with two of my CH3 groups. I draw my CH2, and then I draw out my OH functionality. Now that I have my complete skeleton, I can convert it to a bond line structure. This is why I recommend drawing the partially condensed structure, because it makes it very easy to draw the bond line arrangement. Does this make sense to everyone? Is everyone feeling more comfortable drawing these bond line structures? So this is going to be how we represent structures in this class almost from now, from this point onward.
Quick question.
Yes.
So, similar to my previous question, if you were to draw the OH instead of being angled upward, you can draw it going downward.
Oh, yes, you can just as easily draw it angled downward, and it's the exact same structure.
Okay,
And
that's not an isomer or anything like that. That's just
that's because the carbon-carbon bonds are rotatable, and as a result,
right.
you can draw different. I guess you'd call them rotamers, but they're the same compound.
Okay.
Mm-hmm. Perfect, perfect. Great questions so far. So what we're going to do now is we're going to really practice again drawing some Lewis structures from bond line structures. And the reason for this is because you need to be able to identify hydrogens and identify the number of hydrogens on each carbon, so you can get a sense not only of structural features such as stereochemistry, but also reactivity. So carbon forms 4 bonds. You want to make sure that
You assume it's saturated, right?
Unless it's what was that?
You assume it's saturated unless it's specifically, unless it specifies otherwise, like with hydrogen.
Yeah. So you assume that each carbon is saturated with hydrogens unless there's unsaturation, such as a double bond, triple bond, etc. One other thing that you want to watch out for is you want to check the formal charges on each atom, and you want to make sure that the formal charge on each atom matches the formal charge in your final structure. So in this case, we're going to try to draw a Lewis structure from the following bond line arrangement. So in this case, so this dot has 1 bond currently. So how many hydrogens do we need to add? How many hydrogens do I need to add to this carbon that I'm starting out with?
3.
3. 1, 2, 3. Okay. Now for our second carbon, we have our OH. That's normal. And then this carbon is bonded to another carbon. So how many hydrogens do I need to add to my second carbon to complete it? 1, exactly right. Now for my third carbon, it has 2 bonds. So how many hydrogens does it need? 2, yep, exactly right. Now we have a carbon with a double bond. So how many hydrogens do we need to complete this octet? 1, yep. And now this carbon has 2 carbons attached to it and a double bond. So do I need to put any hydrogens on this carbon? Are any hydrogens necessary? No, not at all. So now we draw out our hydrogens on these methyl groups, and we're finished with our Lewis structure. So essentially the way that you draw out your Lewis structure from the bond line structure is you replace each point with your carbon and you fill in the hydrogens needed for a complete octet. Does this first example make sense?
Yeah.
Perfect. So now let's practice on this second example here. So I'd like you to take about 3 minutes and try and draw out a valid Lewis structure for the following bond line structure. And don't be shy to share your responses using the annotate feature. If you'd like to also share your response in the chat, what you can do is you can type the condensed structure in the chat as well. So you've drawn out the skeleton, you filled in the explicit carbons, and now you're adding in the implied hydrogens necessary to complete the octet. So the response I see looks perfect. So allow me a moment to clear it, and then we'll rewrite this so that way it's all visible when we export this document into Canvas. So first and foremost, let's draw out each of our explicitly noted carbons. Then we fill in our hydrogens to complete the octet. And from that, we have our complete and valid Lewis structure. Does this make sense to everyone so far? Any questions on this example? Okay, so let's keep going now and let's talk about some tricks for drawing Lewis structures from bond line structures. For charged species, you need to be really careful to note that depending on the formal charge, then we may have more or less hydrogens than usual. So for example, looking at the following structure, we have an anion and a cation in this molecule. So first, we're going to replace each of our implied carbons with a carbon symbol. Then what we're going to do is we're going to fill in our lone pairs and add our formal charges. Now that we have our formal charges and lone pairs in place, then we add our hydrogens. So does this carbon right here that the arrow is pointing to, does this anionic carbon need any additional hydrogens?
Yes.
So looking, it has 3 bonds and 1 lone pair. If we go up to an anionic carbon, it has 3 bonds, 1 lone pair. So does it need an additional bond to hydrogen? It doesn't, and this is good as is. And we can show that by looking at the formal charge, where we take 4 minus 3 minus 2, and that gives us a formal charge of -1. Does that explanation make sense? Another way of thinking about it is if we added a hydrogen, we would have more than an octet of electrons surrounding our carbon. Does that make sense to everyone? Perfect. So now we have to add our implied hydrogens to each of our carbons. And now we have our complete Lewis structure from this bond line structure. So the key takeaway is anionic or cationic species. If we have an anion, this anion on carbon implies that we have a lone pair. And because there's a lone pair on carbon, it has less hydrogens than usual. Does this make sense? So let's try to apply what we've learned to the following example. And I'd like you to draw out a bond line structure for the following molecule. And once you have finished processing this bond line structure, I'd like you to take the bond line structure, convert it to a partially condensed structure, and then finally write out the Lewis structure. And I'll pan down a little bit so there's some space. So I'll give everyone about 2 to 3 minutes to try to write out a complete Lewis structure for this molecule. And don't be shy to share your responses using the annotate feature. Remember, as we have an anionic oxygen, you're going to need to be careful about how many lone pairs we place on that oxygen. And we'll discuss this example in about 1.5 to 2 additional minutes. So we've correctly noted that this anionic oxygen has 3 lone pairs and 1 bond. That's very good. And we're now filling in our implied hydrogens. Very good, very good. And don't be shy to chime in the chat with feedback or input. Would anyone have any additional suggestions for this structure? Is there something that we need to include in this structure in addition to what's already written?
What about on the nitrogen? Up there you go.
What about that? So the hydrogens, yes. And what else? What else are we missing in this structure? We have the lone pairs, very good. It's really good that we noted that. And then do we have some formal charges that we need to write? Do we have some formal charges that we need to write?
On the bottom nitrogen.
Yep, exactly right. And on the top, yep. Perfect, perfect. So this structure looks great so far, and I really appreciate the class providing feedback to help one of the students who's drawing the structure along. Let's now clear this and we'll write the instructor solution, which will look exactly like the solution that the students have compiled together. So, first and foremost, we draw out each of our implied carbons. Then we fill in our lone pairs and we add our formal charges. And then we fill in our hydrogens. This carbon has 1. Each of our other carbons has 2 hydrogens, as those carbons have 2 bonds. So we now have the complete Lewis structure for the following bond line structure. Does this make sense to everyone so far? Is everyone comfortable with this example?
Yeah.
Perfect, perfect. So we've developed skills in terms of drawing out valid Lewis structures. What we're next going to talk about is how molecular shape, molecular geometry, and bond polarity impacts molecular polarity. So molecular polarity is the net dipole in our molecule. So the method that I like to use is known as the vector addition method, where bond dipoles are treated as vectors centered along the bond. And if you've taken physics, you're already starting to get a sense of where we're going with this, because we're going to use the head to tail vector addition method. So for example, we can draw the bond dipole for a hydrogen chlorine bond as an arrow pointing towards the more electronegative atom. And as we see, this dipole has a magnitude a value and a direction. Now, the traditional way is you can visibly add the x, y, and z components of each dipole vector together, but there's a better way, and it's called the head-to-tail method. So the way that it works is you draw the first bond dipole vector, you draw the second bond dipole vector, except this time you start drawing your second bond dipole vector from the head of the first. Finally, you draw a final arrow from the tail of vector number 1 to the head of vector number 2, and this arrow is your molecular dipole. Now, throughout this process, you need to make sure that you have the correct geometry. Now, this may seem complicated at first, but in practice, it's quite straightforward. So dichloromethane, CH2Cl2, looks a little bit like this. Let me make this a little bit easier to interpret. So one question that I have to everyone is, what is the geometry? What is the geometry on this central carbon? What is our central carbon geometry? What is our geometry for that central carbon with 4 bonds and 0 lone pair?
Tetrahedral?
Tetrahedral, exactly right. So then, the bond angles in turn are about 109.5 degrees. So I draw my structure respecting that geometry, okay? Then I draw my bond dipoles. So both of my dipoles for my carbon-chlorine bonds are polarized towards chlorine, right? Because which atom is more electronegative? Which atom is more electronegative?
Chlorine.
Chlorine, yep. Okay, so now what we're going to do is we're going to draw out our first dipole. So this will be dipole number 1, okay? So it's pointing down and to the left. I'm then going to draw dipole number 2, and it's pointing down and to the right. And I draw dipole number 2 starting from the head of dipole 1. Now my net dipole, the way I draw my net dipole is I start my arrow from the tail of vector 1 to the head of vector 2. So this is our net dipole. So our net dipole is pointing somewhere like this. So this is our net dipole. Have you seen a method similar to this in previous chem classes? Or does this dipole estimation match what you would expect for your net dipole for this molecule? Yeah, this method is derived from physics. You can also sort of eyeball the net dipole by looking and seeing, well, where are my polar bonds, where are my bond dipoles pointing, and then averaging it together. But I personally like the head to tail method as it makes it very explicit, the location of the dipole. So as we can see, we can estimate our net dipole, and what this tells us is overall this bottom region of our molecule, this region with our chlorines, has more electron density than our top portion of the molecule with the hydrogens. Does that make sense to everyone? So this net molecular dipole tells us the regions that are electron rich and the regions that are electron deficient. Now, what's really cool about this is that based on the position of the dipoles, we can, and based on this head to tail method, we can actually develop a general rule for which molecules are polar and which ones are not. So dipoles cancel only if polar bonds are symmetrically arranged and if they have the same electronegativity. So what this means, and this is your takeaway, symmetrical arrangements of polar bonds with the same electronegativity difference lead to non-polar molecules. So for example, carbon dioxide, we have the same dipole going in opposite directions, and as a result, the dipoles cancel. So carbon dioxide, despite having polar bonds, is non-polar. Now you may say, why does this matter? Well, there's a big difference between a polar and non-polar solvent, a polar and non-polar compound in terms of properties, reactivity. You certainly don't want to run some of the reactions that we're running in this class in a non-polar solvent or in a significantly non-polar solvent, because likely substances won't dissolve. So to talk about how to assign polarity, this is a shortcut that I found. If you think a little bit about the rules and you sort of look at different structures, you'll arrive at a very similar set of conclusions. So a molecule is non-polar, not polar if. So the first condition is if all atoms are bonded to the central atom and they're identical, or if the difference in electronegativity between atoms bonded to the central atom and the central atom is less than 0.4. So if you have non-polar bonds. So if either of these conditions are met and the central atom has no lone pairs, or it has a symmetrical geometry such as linear, trigonal planar, tetrahedral, or square planar, otherwise the molecule is polar. So both of these conditions must be met. Think of it like a checkbox. If both of these conditions are met, the molecule is non-polar. Otherwise, the molecule is polar. Now, one thing that I want you to focus on, one keyword that I want you to focus on when we talk about polarity is this idea of symmetry and symmetrical arrangements of dipoles. Symmetrical arrangements of identical dipoles, symmetrical arrangements of polar bonds and bond dipoles leads to a non-polar molecule. We're going to see some examples of symmetry in this course where your bond dipoles are arranged in your molecule in a way that they cancel out. So do these rules make sense to everyone so far? If not, we're going to see some examples of these rules in practice. But this is sort of a checkbox to determine whether or not you have a polar or non-polar molecule. Any questions before we move on and start applying these rules? Okay, so let's take a look. And so for example, when we look at water, is water a polar or non-polar molecule? Well, first, following our criteria, water has polar bonds and it has lone pairs around the central atom, so it is polar. Additionally, if we add the dipoles together, and we don't have to do formal vector addition every single time, but I'd just like you to tell me, where are bond dipoles pointing? Are they pointing up, down, left, right? Overall, if we look at both of these bond dipoles, what's the common direction that our bond dipoles are pointing? Up, yep. So we draw our net dipole as pointing up. Exactly right, exactly right. So what I'd want everyone to do now is we're going to look at a few examples. Whoops, sorry, one moment. So I'll do the first example, you'll do the second. So we're going to draw the Lewis structure. We're going to show a 3D drawing of our Lewis structure and then indicate our net dipole. So for CH3OCH3, this is dimethyl ether. Not very commonly handled in the laboratory because it's super volatile. Okay, now I'm going to make sure to draw this structure respecting the fact that oxygen is bent and each of my carbons are tetrahedral. So looking at our polar bonds, we have the carbon-oxygen bonds that are polarized towards oxygen. And just like water, both of our bond dipoles are pointing up towards oxygen. Does this first example make sense? So let's work on this next example. And I'd like everyone to take about 2 to 3 minutes to draw out the Lewis structure, draw out the bond dipoles, and then identify the net molecular dipole. And don't be shy to share your responses using the annotate feature. And the Lewis structure looks good so far. One thing I would note, however, is sulfur. What's the geometry of sulfur? Would someone in the chat like to chime in and help provide input? It's bent, right? So then should we try drawing that sulfur instead of linear a little bit more in a bent geometry? And that'll help you see the molecular dipole. Perfect, perfect. Yep, exactly right. And now we can draw our bond dipoles in. And then by adding up our bond dipoles, we can get the molecular dipole. Perfect, perfect. So I'm going to clear this response and then we'll write out the instructor solution. So the Lewis structure for this molecule looks like so. This is known as methane thiol. Not exactly a fun compound to handle because it smells terrible, as most thiols do. Then, now that we have our Lewis structure respecting the bent geometry, we draw our bond dipoles, and that in turn gives us our net molecular dipole, which is pointing towards sulfur. Any questions on this? If not, let's keep going now. In this case, let's look at the following two structures, and let's try to draw out a Lewis structure with a proper three-dimensional drawing, and then we'll draw out our net dipole. So in this first case, we have the following structure. So to draw out our full three-dimensional molecular drawing, here we go. Now, do we have any significantly polar bonds in this molecule? Do we have any significantly polar bonds in this molecule? No, so there's no net molecular dipole because the bonds aren't significantly polarized. Okay, so let's now try and let's look at carbon tetrachloride, and I'd like you to tell me whether carbon tetrachloride is polar or non-polar. So let's try to draw out a structure using the annotate feature, and let's identify whether we have a polar or non-polar molecule. And we'll discuss this example, as likely many of us have seen something similar to this before, in about another 1.5 to 2 minutes.
That top molecule, the 3D molecular structure, is that trigonal pyramidal?
So looking at our central carbon, it has a total of 4 bonds and no lone pairs. So it would be tetrahedral.
Oh, right. Lone pair is what makes it.
Yep, exactly right. Exactly right. So the responses I see for carbon tetrachloride is correct because all the because each of our polar bonds are arranged symmetrically, the bond dipoles cancel out and our molecule overall is non-polar. That's exactly right. So let's showcase that and let's just rewrite the solution, but that's exactly correct. And this really starts to bring up a key idea when it comes to molecular polarity. Just because you have polar bonds, it does not mean your molecule is necessarily polar. Okay, so looking at each of our bond dipoles, because we have a tetrahedral geometry and a symmetrical geometry, and each of our bonding atoms are identical, our bond dipoles cancel. So our bond dipoles cancel out and our molecule has no net dipole. So carbon tetrachloride is actually a relatively non-polar solvent. Does that make sense to everyone? Okay, so let's keep going now. And just to really add to this idea, since the molecular dipole is the sum of all dipoles accounting for bond direction and bond dipole strength, adding more polar bonds does not necessarily increase molecular polarity. Geometry is key. This is why I have you memorize and be familiar with each of the molecular geometries. So, to really demonstrate this link between geometry and overall molecular polarity, let's try drawing a combination of 3 constitutional isomers and stereoisomers for the following molecule. So you can draw either a constitutional or a stereoisomer. One of these isomers is symmetrical and is non-polar. So there are 3 spaces. So I'd like 3 students to try and draw 3 different structures. And one of these structures is non-polar, the other 2 are not. You may have seen this example in your general chemistry courses, but I always like going back to it as it's a great link between geometry and symmetry and polarity. So let's take about 4 to 5 minutes, and don't be shy to share your responses with the annotate tool. And if you'd like to chime in the chat without using the annotate tool, you can also tell me what based on the alkene geometry, which alkene geometry has a non-polar. Which alkene geometry is our non-polar structure. So let's get started with this example, and don't be shy to provide your responses using the annotate feature or to ask a question in the chat or verbally, and I'd be happy to answer any of your questions. And don't be shy to share your responses using the annotate feature, or if there's a question I can address. This is sort of the kind of cumulative example which combines multiple different topics together that you'd see on exams and quizzes. And we'll discuss this example in another 3 to 4 minutes. And the annotate feature is accessible using the View Options tab in the upper black box of Canvas. And don't be shy to share any one of these 3 possible isomers, and your classmates and myself will help fill in the rest. But I'd love for someone to get us started with one of the proposed Lewis structures. Perfect. We have one of those structures. And for the structure in blue, would you like to tell us whether it's polar or non-polar? And could you draw the dipole out, please? Perfect, perfect. There's one more blank structure space. Would someone like to chime in for one of the other structures? So we have two of them so far. We need one more to complete our list. Would anyone in the chat like to help us out? Perfect. So the structure in purple is our trans isomer. There's one other, not a constitutional isomer, but rather a stereoisomer that we can draw. Yep. And that's the cis isomer. Yep. Now for the interesting part. Now that we have the three structures drawn, would someone in the chat like to chime in, or would someone who's drawing like to chime in and tell us which of these structures is non-polar? Which of these structures has dipoles that are canceling out, that are in opposite directions?
Two.
Two, yep, exactly right. Perfect, perfect. So thank you. This was a great discussion, and I'm going to clear the annotation and then I'll provide the instructor solution. So for each of our Lewis structures, so in the first case, we have a genuine constitutional isomer, and our net dipole, because we have polar, sorry about that, one moment. Because we have polar carbon-bromine bonds, our net dipole points towards the bromines. Our second structure is the trans isomer. And in this case, as we notice, this molecule is symmetrical and our dipoles are arranged symmetrically. So even though our dipoles are not associated with bonds the same atom, as we can see, our two dipoles are identical in magnitude and opposite in direction. So we have no net dipole. Because it's a symmetrical arrangement of polar bonds. We'll see a lot more examples like number 2 later on in this chapter. Our last example, so this is the trans isomer. Our last example is the cis isomer, where both of our bromines are arranged on the same side of our double bond. And as a result, our net dipole is pointing up. Does this make sense to everyone? So this is a clear example where molecular symmetry leads to canceling dipoles and a net nonpolar molecule. So subtle differences both in structural connectivity and shape, stereochemistry, directly impacts molecular polarity and properties. So, the last major topic that we're going to discuss in this lecture module has to do with chemical bonds. So we're going to talk a little bit about estimating bond length and strength, because in chemical reactions, we're making and breaking bonds, right? So you want to know which bonds are easiest to break, which bonds are strong, which bonds are weak, which bonds are favored to form. Because formation of stable bonds can often be a driving factor in many reactions. Identifying weak bonds can help you identify potentially reactive bonds. It provides you a guideline to draw reasonable reaction mechanisms and explain how chemical reactions occur from an energetic perspective. Okay, so a chemical bond can be thought of as shared electrons or the result of an orbital overlap. So these are our two models that we have. Electrons in a chemical bond are stabilized by the nuclei of each atom and thus are lower in energy. Bonds are stable for the most part. Now for bond energy and bond enthalpy, this is a tabulated value that we're going to use to estimate bond strength. It's the energy required to dissociate a bond into its component atomic elements in the gas phase. Bond energies are positive, as it costs energy to break a bond. Has everyone seen these bond energy values before? Is this something that looks familiar from general chemistry?
Yeah.
Perfect. Okay, just checking. Always have to make sure to just get a sense of what topics have been covered previously. So bond energy in general increases with an order of importance. First and foremost, bond order. Triple bonds are stronger than double bonds, which are stronger than single bonds. So for example, a triple bond is stronger than a double bond, which is stronger than a single bond. Likewise, for example, if you calculate a bond order, let's suppose that you're looking at a molecular orbital diagram and you calculate your bond order. Remember the example where we're looking at a nitrogen-oxygen bond? So we filled in the structure for nitrogen monoxide and we calculated our bond order to, in this case, be 8 minus 3 over 2, which is 2.5. This 2.5 bond order, following that logic, and just to make sure we understand this idea, so if we compare this 2.5 bond to, for example, a nitrogen-oxygen double bond, which has a bond order of 2, which bond is stronger? The bond in nitrogen monoxide with a bond order of 2.5, or the bond in, for example, NO2 or a nitro group with a bond order of 2? Which bond is stronger? 2.5, right? Yep, exactly right. The larger your bond order, the stronger your bond, and the more energy is required to break that bond. Okay. This idea of fractional bond order will come up when we start talking about resonance. So, bond length. In general, short bonds are stronger. A closer sharing of electrons between atoms leads to a stronger bond. So for example, a carbon-fluorine bond is stronger than a carbon-chlorine bond. Now, why is that? We're also looking at, we have smaller orbitals are lower in energy and they overlap more efficiently. So just to show this, so if we have a carbon 2p overlapping with a fluorine 2p orbital, So not only are the 2p orbitals, well, let me just write this as an sp3, just as an example, There's no particular reason why I chose an sp3. This is just an arbitrary carbon orbital. We're really focusing on the fluorine here. The 2p orbital is relatively low in energy. That's why our overlap leads to a low energy bonding orbital. Now, if we move and we look at a carbon-chlorine bond, is chlorine going to be using a 2p orbital for bonding? What is the outermost orbital for chlorine? What is the outermost orbital for chlorine? So instead of a 2p, since chlorine is bigger, what orbital will we be using? 3p, yep, exactly. And the 3p orbital is bigger. And as a result, because we have a larger orbital, we have a weaker overlap. And most important, and as well, our bond is going to be longer because this 3p orbital, as we can see, is visibly farther from the nucleus. And just to add on to the issues, if we look at, for example, our relative orbital energy, our 3p orbital is way higher in energy. And as a result, because our 3p orbital is higher in energy, that in turn means that our bonding orbital is higher in energy. So we have a higher energy bonding orbital, and in turn, that means this is a weaker bond. Does that make sense to everyone? Does everyone see why longer bonds involving larger atoms are weaker and shorter bonds involving smaller atoms are stronger? Does that make sense to everyone? See, valence bond theory does actually help you understand a lot of these trends. And that's why we teach it. So bond electronegativity. Polar bonds are stronger as they have more pseudo-ionic character, and we end up with this attractive interaction. So for your hydrogen-fluorine bond, we generate a lot of partial negative character on fluorine and partial positive character on hydrogen, and this leads to an attractive interaction between atoms. At oxygen-hydrogen bond, the dipole is weaker, so as in turn, our partial charge is less. Does that make sense to everyone? Just remember this idea, ionic bonds are strong, so bonds with ionic character, bonds with an uneven distribution of charge, with large partial charges, are also going to be strong due to this attractive interaction between our partially charged atoms. Okay, so why does bond strength increase with bond order? Well, bond strength increases as we have more electrons shared between atoms and there's a greater orbital overlap. Triple bonds involve sharing 6 electrons, so we'd have to separate 6 electrons shared between atoms. So if we're looking at a nitrogen-nitrogen triple bond, it takes a lot more effort to separate 6 electrons shared between atoms than it does 2. Further, if you look at it from an orbital picture, we have a large amount of orbital overlap. And as we see, because we have 3 orbital overlaps, 3 bonding interactions, it takes a lot of energy to break these very strong, to break these bonds, to break these bonding interactions between our orbitals. Does that make sense to everyone? Why larger bond order, harder to break bond? Now, in terms of, one moment. So in terms of why does bond strength increase as bond length decreases? Well, electrons in shorter bonds are held closer to the nucleus, and short bonds are the result of close overlap of orbitals. Longer bonds have poor orbital overlap and higher energy orbitals, resulting in a high energy bond. So just to show an example, if we looked at HBr versus HF. So in HBr, for example, the hydrogen's this little tiny orbital, and then we have this gigantic bromine with just a very weak orbital overlap. So here's our hydrogen and here's our bromine, and we have a very weak overlap. While for our hydrogen fluorine bond, we have our hydrogen, we have our relatively small fluorine, and that in turn facilitates an efficient, strong orbital overlap. And this is also reflected in the orbital energies as well. Does this make sense to everyone? Short bonds using small atoms, strong, generally. There are some exceptions, and that's due to additional orbital effects at play. So when we talk about bonds and orbitals, remember how we said bond strength is based on the relative energy of orbitals used, right? High energy orbitals, large orbitals, weak bonds. So as orbital energy increases, bonds formed using that orbital are less stable and easier to break. So for hybrid orbitals, the more S character a hybrid orbital has, the shorter and lower energy that orbital is, right? So if we think about it, sp3, long, sp2, it's a little shorter and a little bit fatter. And sp orbitals are really short and really fat. Let me make this a little bit. There we go. This is just to help you visualize these trends. So the sp orbital is the shortest and it's also the lowest in energy. So for bonds of the same bond order, bonds made using an sp orbital are going to be lower in energy and stronger. Why? sp hybridized orbitals have more S character and are lower in energy. And shorter bonds involving an sp hybridized atom are in turn shorter and stronger. So this is the bond strength section that you need to know. In general, bonds involving an sp hybridized atom are stronger than sp2 hybridized atoms, which are stronger than sp3 hybridized atoms. And the thing you need to note is that you need to consider both atoms. You need to consider both atoms. So what do I mean by that? Well, let's take a look at the following table. So if we look, for example, in methane, so methane is sp3, it has a carbon-hydrogen bond. So we have an sp3 orbital overlapping with a 1s orbital. And it has a bond strength of about 439 kilojoules per mole. You can also memorize, you can also be familiar with the kilocalories. I personally like kilojoules, where you're going to take physical chemistry eventually, you're going to take biochemistry eventually. Joules and kilojoules are the standard. Okay, now let's look at ethane. So let's pay attention to ethane. So a carbon-carbon sp3-sp3 bond has about 337 kilojoules required to break that bond. So what's the first thing we notice when we compare a carbon-hydrogen bond and a carbon-carbon bond? Which bond is stronger? Which bond is stronger? Carbon-hydrogen or carbon-carbon? Carbon-hydrogen, yep. Would anyone like to make a suggestion as to why that is?
Because it has that SP.
Yes.
I mean the 1s.
The 1s, yes. And is it high? Is that a high or low energy orbital?
High energy.
The 1s?
Or lower energy. Hold on. I'm backwards.
So stable bonds which have a high bond enthalpy are composed of low energy bonds made from the overlap of low energy orbitals. So then with the hydrogen 1s orbital, is it low energy or high in energy?
Low in energy.
Exactly right, exactly right. Now, here's where things get interesting. Looking at a carbon-hydrogen bond for an sp3, it's 421 kilojoules. We're not going to explain this gap between methane and ethane just yet. This requires a little bit more nuance that we'll talk about in the next few chapters. You'll be able to answer this trend by the end of the class, but this is very nuanced. What's not so nuanced is if we look first and if we look next at a carbon-carbon double bond, as we notice, the bond energy is 728 kilojoules. Does everyone see the massive jump when we go from a single to a double bond? As we increase bond order, does everyone see how our bond strength jumps up? And does everyone see how our bond length also decreases? Does everyone see how the bond length also drops?
Yeah.
Okay, now this is the next part that I want us to consider. When we look at the carbon-hydrogen bond for an sp2 carbon, we notice its bond enthalpy is 464 kilojoules. If we compare that to our carbon-hydrogen bond for our sp3 hybridized carbon, is our bond enthalpy greater or less for an sp2 carbon? So is this sp2 carbon-hydrogen bond stronger or weaker than an sp3?
Stronger.
Stronger. Now, what's really cool is that our bond strength increases and our bond length decreases. And we see this quite clearly where if we compare our sp carbon-hydrogen bond to our sp3 carbon-hydrogen bond, which bond is not only shorter, but also stronger? Which bond is shorter and stronger, the sp3 or the sp carbon-hydrogen bond? The sp, exactly right. The more S character we have, in general, sp hybridized atoms will have lower energy bonding orbitals, which in turn leads to lower energy bonds. And because the orbital is shorter and stubbier, we end up with a shorter bond. Does this make sense? Does this make sense?
Yes.
Perfect. So this is the payoff for discussing orbitals, orbital theory, and valence bond theory. It allows you to explain these really important trends in how hybridization affects bond strength. So hybridization is something that you absolutely have to know because we're going to hammer on this point not only in this chapter, but in subsequent chapters. So this is a great stopping point. So that's it for our supplemental lecture. So I'll pause this recording.